Good afternoon. I am Shalli Singla from GPC Pune Majra. Today my topic is conservation of angular momentum and its examples. So, first of all, we will define torque and angular momentum. As we have discussed in the earlier lecture, torque may be defined as the product of, it is denoted by tau, and it is the product of moment of inertia I of the particle rotating body and angular acceleration alpha, whereas angular momentum is denoted by a symbol L, and it is the product of moment of inertia of the rotating body I into omega. Omega is the angular velocity of the rotating body. Another relation of torque is with the force. Torque is equal to r vector cross f vector. F is force, this is in the linear motion, whereas torque is the twisting effect of the force in the rotational motion, and angular momentum L is equal to r vector cross p vector. P vector is the linear momentum in case of linear motion, whereas L vector is the angular momentum in for the rotational motion. So, there is now we will take the relation between torque and angular momentum. So, from the Newton's second law of motion, we have relation between force and linear momentum P. The force is defined as the rate of change of linear momentum with respect to time, means whenever the linear momentum is changing with the time, that change is given by force. So, if we correlate this with the rotational motion, force is analog of force in the rotational motion is torque, and analog of linear momentum is angular momentum L. So, we have torque T tau vector is equal to dl upon dt. So, this is the relation between torque and angular momentum. Now, we have topic of conservation of angular momentum. As we have conservation of linear momentum, same is the case with the conservation of angular momentum. This law states that the law of conservation of angular momentum states that if no external torque is acting on a rotating body, then its total angular momentum remains constant. So, as we have from the Newton's law that if no external force is acting on a system, then its linear momentum remains constant. This is the law of conservation of linear momentum. Same is the, so we have if torque acting on a system is 0, then we have L is constant. L is the angular momentum. So, we can prove it. So, we have its proof. The relation between L and T torque is equal to dl upon dt. Both are vector quantities. So, we have torque vector is equal to dl vector upon dt if there is no external torque, means tau is equal to 0. So, dl upon dt is equal to 0. Now, if differentiation of angular momentum with respect to time t is equal to 0, it means L is not changing with the time, it is constant. So, we can say L is equal to constant. Anything which is constant, then its differentiation derivative with respect to time is 0. So, L is constant. Now, we can say L is equal to I into omega. L is the product of moment of inertia I of the rotating body and angular velocity omega. So, I omega is constant. So, we can, in other words, I1 omega 1 is equal to I2 omega 2. So, if we change the moment of inertia of the body from I1 to I2, then its angular velocity will change from omega 1 to omega 2. We can also say that I is inversely proportional to angular velocity omega. If angular velocity is more, then moment of inertia will be less and vice versa, or omega is also inversely proportional to moment of inertia I. So, this is a proof of the law of conservation of angular momentum. So, next is the examples of conservation of angular momentum. So, the first example is, suppose we have a person it is standing on a rotating table. This is a table which is rotating. suppose its angular velocity is omega 1 and the person is having some weights in his hands and he stretches his arms outside. So, the radius of his arms is r1. Now, as we know that I1, I is the moment of inertia, this is equal to m into r square. M is the mass of the person who is standing on the rotating table. I is equal to m into r square. I1 can be written as m1 into r1 square. Since the mass of the person does not change, only radius of gyration r1 is changing. So, I is dependent on r1. So, if he stretches his hands outside, then r1 is more. So, I1 will be more. So, another case of it is in another diagram. Let us draw some. Now, if he stretches his hands inwards, then its radius of gyration is r2 and its angular velocity is changed from omega 1 to omega 2. Now, we can say I2 is equal to m2 into r2 square, m into r square. M is constant, m is the mass of the person who is standing on the turntable. Now, we know that I1 omega 1 is equal to I2 omega 2. So, omega 2 upon omega 1 is equal to I1 upon I2. So, the ratio of omega 2 upon omega 1 is equal to ratio of moment of inertia. As I1 is more than I2, I1 is greater than I2. So, omega 2 is greater than omega 1. So, we can say if a person who is standing on the turntable stretches his hands outside, then its angular velocity will get increase. If he stretches his arms inside, then its angular velocity omega 2 is more as compared to omega 1. So, this is the first example. The second is ice skater or a ballet dancer stretches his or her body inward to increase their speed, their angular velocity. So, if an ice skater or a ballet dancer has to increase their angular velocity, then he or she has to stretch his hands as well as legs in the inward direction. If he or she stretches his or her body outside, then angular velocity gets decreased. So, this is the second example of law of conservation of angular momentum. The third one is a diver who is diving inside the water, folds his body to dive deep inside the water. So, if a diver has to dive deep inside the water, then he has to fold his entire body. And the next example is the speed of inner layers of a whirlwind is alarmingly high. So, we can draw a diagram. Suppose we have a whirlwind who has concentric layers of the air. So, we can say that this is the inner layer and this is the outermost layer. If we compare the innermost layer with the outermost layer, the radius of the innermost layer is R1 and outermost layer is R2. So, R1 is less than R2. Now, I1 is equal to directly proportional to R1 square and I2 is directly proportional to R2 square. I1 is the moment of inertia of the inner layer and I2 is the moment of inertia of the outermost layer. So, we can say I1 is less than I2. Since I1 omega 1 is equal to I2 into omega 2, so omega 2 upon omega 1 is equal to I1 upon I2. So, we can say omega 2 is greater than omega 1. So, it means the innermost layers have angular velocity omega 2 and outermost omega 1 and outermost layers has velocity omega 2. So, omega 2 is less as compared to omega 1. And the next example is, if a planet moving in an elliptical orbit comes near to the sun, its angular velocity increases. So, we can draw another diagram. So, this is another an elliptical orbit. The sun is lying at the center of the orbit and we have a planet which is moving in the elliptical orbit. Now, at this point the distance is r1 and at this point the distance is r2. We can clearly see from the picture that r1 is greater than r2. So, we can say that I1 is greater than I2. If I1 is more as compared to I2, we can say that omega 1 is less than omega 2. It means whenever a planet revolving in an elliptical orbit comes near to the sun, its angular velocity increases. So, these are some applications of the law of conservation of angular momentum. So, let us take some example. What will be the duration of a day if the earth shrinks to 1/60th of its original volume. Mass remains constant. So, we have earth and its if its volume is decreased to 1/64 of its original volume, we have to find the duration of the day. We know that I1 omega 1 is equal to I2 omega 2. So, this is before shrinkage. We can say L1 is equal to L2. L1 is the angular momentum before shrinkage, and L2 is angular momentum of earth after shrinking. Now, we know that I1 is equal to mass of the earth into radius of the earth r1 square into omega 1, whereas I2 is equal to mass of the earth radius r2 square into omega 2. Here we have taken mass same on the both side, which is m, because mass is not changing and it is same. Now, m cancels with the m, r1 square into omega 1 is equal to 2 pi upon t1. The angular velocity of the earth is equal to 2 pi upon time period t1. This is equal to r2 square into 2 pi upon t2. 2 pi is cancelled out with 2 pi. So, we can write t2 upon t1, the ratio of the time t2 upon t1 is equal to r2 upon r1 whole square. So, now we have to find the ratio of r2 upon r1. Now, we know that volume is decreased by 1/64. If original volume is 64, V1 is original volume 64, V2 remains 1. The ratio of V2 upon V1 is equal to 1 upon 64. Now volume V2 is equal to 4 upon 3 pi R2 cube and V1 is equal to 4 upon 3 pi R1 cube. Because earth is a sphere, so we have taken the volume as that of a sphere. 4 upon 3 pi and 4 upon 3 pi has been cancelled. R2 upon R1 whole cube is equal to 1 upon 64. So from this we have R2 upon R1 is equal to 1 upon 64 raised to power 1 by 3. 1 by 64 raised to power 1 by 3 is equal to 1 upon 4. So the ratio of R2 upon R1 is equal to 1 by 4. If we put its value 1 by 4 square, then we have T2 upon T1 is equal to 1 upon 16. So we can say T2 is equal to T1 upon 60. T1 is time of earth before shrinking. It is equal to 24 hours upon 16. So it is equal to 1 by 1.5 hour. So we have the time after shrinking is equal to 1.5 hour. So this is some example related to the law of conservation of angular momentum. Let us take another example. A boy is standing on a rotating table form with his arms extended and rotating. With the frequency 0.40. When he draws his hands in, the frequency is 0.64. Find the ratio of moment of inertia in both cases. So we have, let us draw a diagram. This is a boy who is standing on a rotating table. He has his arms extended and he is carrying weights in his hands. In another case, he is standing on the table, rotating table, and having hands having weights is in hands and stretched his arms inside. Uh, Here the moment of inertia is I1 and angular velocity is omega 1. In this case, moment of inertia is I2 and angular velocity is omega 2. Now we are given that he has a frequency n1 is equal to 0.40 before with his arms extended, and n2 is equal to 0.64. This is the frequency when he has folded his arms inside. Now omega